Page 1. So this is all about permanent magnets and drawing the magnetic field. So key ideas with permanent magnets is you need unbalanced electron spin, which I'm not sure actually is in here anywhere now that I'm thinking back to it. Unbalanced electron spin, right? So if you remember back to those different orbital levels, you have 1, 2, 3, 4, 5. So that would be a d orbital there, right? D can have 10 locations. P orbital, that's a p orbital. P orbital can have, no, D's right. D's right. I really should just start this over, but I'm not going to. D, 10 spots. And so as those electrons fill, they're all going to be up spin electrons. This is an example of unbalanced electron spin. I've got 5 up spin electrons and no down spin. Maybe I've got 1, 2, I think that's iron there, right? 1, 2, 3, 4, 5, 6, 7. I know iron's just one of those. So that would be iron there. But anyway, that's that unbalanced electron spin. Then you have that thing called domains. So then we get to domains. If those unbalanced atoms are all in the same direction in a domain, and then to make it an actual magnet instead of just a magnetic material like a nail, you need to align those domains. So 3 things: unbalanced spin, domains, and aligned domains. So let's go through the questions. Permanent magnet. Here we go. You can see in the middle here, I've got a little arrow, and that's going to be a north and a south to each of those. Those arrows are showing that. Where's the north pole of this magnet? So the north pole is where all the norths kind of end up. So D would be over here on the north side of that magnet. And another way to think about this is kind of around it. What would a compass do? So those are the domains inside. But if I were to put a compass right here, which way would the compass point? Well, since that's a south, the north side of the compass is going to be attracted to that. So the north side of a compass is always going to point at the south side of a magnetic pole. And then it would point away from that. And then if you're over here on the sides, it would be pointing kind of that and creating that kind of magnetic field. Okay, we'll draw this later, but that's just the idea of a compass. And it's a little confusing because that's inside the magnet is the domains, outside is the compass direction. All right, so permanent magnet, the picture be made of anything but. This one you just got to know. Later on in the guide, we actually give you the numbers, and that's a way better way to do it. But for this particular one, nickel, cobalt, and iron are all ferromagnetic materials. Keyword there, ferromagnetic materials. And so they could become magnets, whereas copper is not. Copper cannot be aligned. I'm not even sure it's got domains, but it cannot be aligned. And I don't think it's got very unbalanced electrons either. So copper's bad for that. Or non-existent, doesn't work. And so if iron, so now we're back down to an iron. What can an iron skillet? So why can't the iron skillet pick it up? It's because the domains are not aligned. In the iron skillet, the domains are not aligned. It's a magnetic material. It has domains, but they're not aligned. And so it doesn't have the magnetic field around it. So it's not a magnet. It's not going to interact with other metal things like paper clips or iron things like paper clips until one of those things has their domains aligned and it becomes a magnet. All right, when playing darts, some bar magnets with one of the magnets breaks in half. What happens to the polarity? Well, if I've got that magnet here with a north and a south pole to it, if I break it, right, remember it's made up of all those little domains in there. So each domain has a north and a south pole. So if I break that magnet with the south pole on one side and a north pole on the other, I'm going to expose those other domains there. So that's going to leave some south poles exposed and some north poles exposed, and I get 2 little magnets. Now, they are smaller, and so it will be a weaker magnetic field. I'm not sure why I'm using red here. I'm just going to stick with it because I'm already doing it. But all right. So draw the magnetic field around these magnets. Can you just got to draw lines from the north to the south? And then with a horseshoe magnet, they would be nice even lines. Maybe you could get the one out there on the edge. That would be even. And then they point from north to south. Magnetic field lines tell us the direction that a compass would point. And so they point from the north to the south. Now, a bar magnet's going to look actually right down below there. There you go. So we're going to go from the edge around. I go from this side around. There we go. And then maybe even got a little one right there. And then we want to draw the arrows. Which way would the compass point? And it would point from the north to the south. So we're going to direct all those lines towards the south magnetic pole. All right. And so then finally use the following diagram. We want to label north and south. Remember, magnetic field lines are pointing from north towards south. So that's going to be a south pole, leaving that one. And then if you look here in between, it looks like it's broken. So we actually have another north and a south there. Greatest strength, right? Remember, density is the strength. So where's it closest together? It looks like B. Again, just use the picture. Don't try and say, oh, close to the magnet, far away from the magnet. Because honestly, we're keying it for line spacing. So B is the closest together, followed by C, followed by D, and then A way out there. Since there's no fields drawn, right? If we kept drawing the fields, it might not be, but since there's no field lines, A is the weakest out there. All right, that is page 1.